Next, we are going to study about properties of colloids, one of the most important section coming in the surface chemistry chapter. The first property of a colloid is colligative properties. We already studied about colligative properties in solution chapter. What do you mean by colligative properties? These are the properties actually exhibited by dilute solutions, and these are the properties which depends on the number of solute particles irrespective of their nature. So, mainly colligative properties depends on the number of solute particles, and these are actually the properties of a true solution or dilute solution. So, when we compare, the colloids can also exhibit colligative properties, but when we compare, if you take a true solution in 1 molar concentration and a colloidal solution with the same 1 molar concentration, and if you compare the colligative properties, colloids will be having lesser or lower value for the colligative properties. Why? The reason is colligative properties are the properties which depends on number of solute particles. So, when we compare with true solution, in true solution the size of the particle is very small, but in the case of a colloid there is aggregation of particles and the size of the particle will be larger definitely. So, the number of particles will be less in the case of colloids. That is why the colloids will exhibit lower value for colligative properties. Now, the second property is Tyndall effect. We know what is Tyndall effect. It is one of the main property exhibited by colloids. When a beam of light, when it is passed through a colloidal solution, what happens? We can see the path. The path of the light will be illuminated, or we can see the path of light. Why we can see the path of light? This phenomenon is called Tyndall effect. And what is the reason for this Tyndall effect, or what is the reason for this illumination of path? We know that colloids are having larger size. So, when light radiations fall on colloidal particles, there is scattering of radiation. So, due to scattering of light, the path of light becomes visible, and this phenomenon is known as Tyndall effect. So, Tyndall effect and the path traced is called Tyndall cone, and this effect was first observed by Faraday and studied in detail by Tyndall. Now, there are two main conditions required to exhibit Tyndall effect. The first one is the diameter of the dispersed particles is not much smaller than the wavelength of the light used. Simply what we can say, the size of the particle or the diameter of the particle should be large enough to scatter the light. Now, the second condition is the refractive indices of dispersed phase and dispersion medium must differ large in magnitude. So, these are the two conditions required to exhibit Tyndall effect. Now, the third property of colloids, that is color. Colloids can exhibit color. Now, the main reason for, or the color exhibited by the colloid mainly depends on the wavelength of the scattered light. We know that when light radiations fall on colloidal particles, there will be scattering of light. So, the scattered light wavelength, the wavelength of the scattered light is one of the factors that determines the color of the colloids. And the wavelength of the scattered light, this wavelength again depends on what? The size of the particle and the nature of particles. And there is one more factor which depends on the color of the colloidal particle is the way in which we receive the scattered light or transmitted light. So, these are the three factors which affects or which depends on the color exhibited by colloids. For example, the finest gold sol is red in color. As the size of the particle increases, it appears purple, then blue, and finally becomes golden yellow. Now, the next property of a colloid is Brownian movement. You can see the diagram as it is shown in the diagram. Brownian movement means it is a continuous zigzag motion of molecules. What do you mean by zigzag motion? See the diagram. If one colloidal particle is moving in this direction, the other one will be moving in another direction. The another one in another direction. So what happens? They will be always continuously colliding each other, bombarding each other. So here the term that we are using here is bombardment. So due to this random motion or zigzag motion, the particles will be colliding each other. So Brownian movement, when a colloid solutions are viewed under a powerful microscope, the colloidal particles appear to be in a state of continuous zigzag motion. This continuous zigzag motion is known as Brownian movement. And this Brownian movement depends on the size of the particle, because if the size is very large, the movement will be less. It won't be that much random. Now, and the viscosity of the solution. If the viscosity is high, like honey and all, what happens? Movement will be lesser, or Brownian motion or movement will be less. Now, so this phenomenon has been explained due to the unbalanced bombardment of particles. So the reason for the zigzag motion or the Brownian movement is the unbalanced bombardment of colloidal particles. And one of the main consequences of this Brownian movement is, just take the example of sand in water. It is a suspension. If you keep the sand in water mixture, very easily the sand particles will settle at the bottom. But if we are continuously stirring the mixture, what will happen? Will the sand particles, will it be settling at the bottom? No. Such a stirring effect is there in colloids. This Brownian movement means the continuous bombardment of or collision of particles. So the Brownian movement has a stirring effect which does not permit the colloidal particles to settle at the bottom. And this is responsible for the stability of colloids. For the stability, the reason for the stability of colloid, one of the reasons is this Brownian movement or zigzag motion. Now, the next colligative property is one of the main property of a colloid, that is charge. All the colloidal particles carry charge, but either it will be negative, the whole colloid will be negative, or the whole colloid will be positive. So the nature of this charge is same on all colloidal particles and may be either positive or negative. And the presence of equal and similar charges on colloidal particles is largely responsible for the stability of colloidal solution. So just now we told Brownian movement is one of the partially we can consider as the reason for the stability of a colloid, but one of the solid reason for the stability of a colloid is the charge on colloidal particles. And this similar charge, we know that the similar charge will repel each other, and this similar charge will cause repulsive forces between the charged particle, and that will prevent them from aggregating, prevent them from settling at the bottom. And these are the few examples of positively and negatively charged colloids. Let us see. All the metal oxides are positively charged salts, like arsenic oxide, CrO3, Fe2O3, TiO2, etc. So all the metallic oxides, then basic dyestuffs and hemoglobin present in the blood, they are positively charged colloids. Now examples of negatively charged colloids, all the metal salts and their sulfides. For example, copper salt, silver salt, gold salt, all these are negative colloids. Then arsenic sulfide, antimony sulfide, cadmium sulfide, all the sulfides are negative colloids. Now, acidic dyestuffs are negative colloids. Then starch, gum, gelatin, clay, charcoal, etc. All these are examples of negative colloids. We have to study all the negative and positively charged colloids. Now, what is the reason for the charge exhibited by these colloids? One of the main reasons for the charge exhibited by a colloid is due to preferential adsorption of or the formation of electrical double layer. So, the main reason for the formation of charge, the main reason for the charge exhibited by colloidal particle is due to preferential adsorption or formation of electrical double layer. The more common reason is the preferential adsorption. Now, we will see what is meant by preferential adsorption. So, here we are considering the reaction between silver nitrate and potassium iodide solution. What happens when silver nitrate reacts with potassium iodide solution? We get the precipitate of silver iodide. So, here we are considering two cases of this reaction. In the first case, you have to listen carefully. In the first case, in a beaker I have potassium iodide solution. To this solution, I am adding silver nitrate from a test tube dropwise. So, what happens? Whatever silver nitrate coming from this test tube will be reacting with potassium iodide and forms AgI precipitate. Okay, then when you compare the AgI precipitate forming here with the dispersion medium, here what is the dispersion medium? Potassium iodide. So, here when you compare the precipitate of AgI formed with the dispersion medium, that is potassium iodide here, which is the common ion present in both iodide ion. So, what happens is that first we are getting a precipitate of AgI in this beaker. It is a precipitate, there is no charge. But this AgI precipitate has a tendency to adsorb the common ion from the dispersion medium. Which is the common ion present here? Potassium iodide has I minus, AgI also has I minus. So, this AgI precipitate will adsorb the common ion, that is I minus, from the medium, so that it becomes negatively charged. So, now did you understand how it is getting negative charge or how it became charged? So, this is a negative layer. So, this layer will be tightly held or firmly held layer called fixed layer. So, the precipitate will be holding the first layer of this I minus tightly, and definitely this negative layer or I minus will be having a tendency to adsorb. Now, which is the remaining ion present here? K plus ions. So, this I minus layer or negative layer has a tendency to attract, but it won't be holding tightly. It has a tendency to attract the positive ions, that is K plus ion, near to it. But that layer will be called as diffused layer. It won't be tightly held layer. So, now we can see the first layer called fixed layer of negative ions, which will be tightly held by the AgI precipitate, surrounded by a layer of positive charge, which is called diffused layer. So, now we have an electrical double layer. This is what we call as formation of electrical double layer, and the potential difference between the fixed layer and the diffused layer is known as zeta potential or electrokinetic potential. So this is about the first case. Let us see the second case. That means in the second case, in the beaker we have silver nitrate solution. So in the beaker we have silver nitrate solution. We are taking silver nitrate in the beaker. To that we are adding potassium iodide from the test tube. So what happens is that when silver nitrate reacts with potassium iodide, here also we are getting the precipitate of AgI. But when you compare the AgI precipitate formed here with the dispersion medium here what is the dispersion medium? AgNO3, which is a common ion here. If you compare the precipitate and the dispersion medium, it is Ag plus ions. So the AgI precipitate which is formed here has a tendency to absorb the common ion from the dispersion medium here, which is the common ion present, Ag plus ions. So here the first layer or the fixed layer of positive ion or Ag plus will be formed, and this positive layer has a tendency to attract the negative ions from the surroundings. But the second layer will be a diffused layer, and the potential difference between these two layers, the fixed layer and the diffused layer, will be called as electrokinetic potential or zeta potential. And this is the reason for the charge exhibited by colloidal particles, the preferential adsorption of common ion from the dispersion medium and formation of electrical double layer. So this is about Helmholtz electrical double layer and zeta potential. Now this is the way how we are representing the charged colloid. So AgI precipitate, if it is absorbing I minus ion from the surroundings, this is the negative colloid. AgI bar I minus means AgI is absorbing I minus from the medium, so it will be a negative colloid. Now the last property of a colloid is electrophoresis. In electrophoresis, this is the apparatus setup. Here we are using a U-shaped tube, and at both the ends there is electrodes, and we are applying voltage here. Here we have platinum electrode at both the ends. Now we are filling the colloid, which is carrying either positive charge or negative charge inside this U-shaped tube. And when we apply the potential, what happens, depending on the charge of the colloidal particles, they will be moving towards oppositely charged electrodes. For example, if the colloid is positively charged, it will be moving towards negative electrode. If the colloid is negatively charged, it will be moving towards positive electrode. And this movement of colloidal particles towards oppositely charged electrode under the influence of an electric field is known as electrophoresis. And by electrophoresis we can prove the charge of colloidal particles also. So the movement of colloidal particles under the influence of an electric potential is called electrophoresis. And by means of any method, if we are preventing the flow of this colloidal particles, only what will be moving? The solvent particles. If the solvent particles are moving, then it will be known as electroosmosis, because in osmosis there is movement of solvent particles only. Otherwise it will be known as, if the colloidal particles are moving under the influence of an electric field, it will be called as electrophoresis. Now the next property of a colloid is coagulation. The stability of, we already studied that lyophilic colloids are stable and lyophobic are unstable. The main reason for the stability of a lyophilic colloid is around the lyophilic colloids there will be a layer of solvent, and this layer is absent in the case of lyophobic colloids. So, the stability of lyophobic sol is due to the presence of charge on the colloidal particles. If the charge is removed, the particles will come near. Once we remove the charge of the colloidal particles, what will happen? They will come close to each other, they will become precipitate, and they will settle under the force of gravity. The settling of colloidal particles is known as coagulation or precipitation or flocculation. So, how we can convert a precipitate into colloid? By peptization. If you add an electrolyte to a precipitate, the precipitate becomes colloid. Here it is coagulation, that is, it is a conversion of a colloid into precipitate. How we can convert a colloid into precipitate? By removing the charge. How we can remove the charge? There are so many methods for coagulation. Coagulation is also known as flocculation or precipitation. The first method for coagulation is by electrophoresis. Just now we explained, when the colloidal particles, depending on their charge, they will be moving towards oppositely charged electrodes, and when they reach the oppositely charged electrons, the charge will be neutralized and they will be settling, they will be coagulating, they will be precipitating at the bottom. And the second method is by mixing two oppositely charged salts. If we mix a negative colloid with a positive colloid, neutralization will be taking place, the coagulation or precipitation will take place. And the second one is by boiling. What happens on boiling? Colloidal particles are charged particles due to the formation of electrical double layer. So, if you boil a colloid, what happens? These layers will be disturbed, so charge will be removed. And the next method is to remove or for coagulation is by persistent dialysis. Usually dialysis is used to remove impurities, but traces of electrolyte is required for the charge of the colloidal particles. So, if you are doing persistent dialysis, all the electrolyte present in the colloid will be removed, charge will be removed, that will be converted into precipitate. And the next one is by the addition of electrolytes. And if a colloid is positively charged, when we add electrolyte, the colloid will attract the oppositely charged ion from the electrolyte and will be getting coagulated. Now, coagulation by the addition of electrolyte, it is governed by Hardy-Schulze rule, that we can understand by using an example. For example, if a colloid, if it is negatively charged, suppose if we have a colloid which is negatively charged, and suppose if I am adding NaCl electrolyte to this, what will happen? This negatively charged colloid will attract this Na plus ions from the electrolyte and they will be neutralized and they will be getting precipitated. To the same negatively charged colloid, if I am adding barium chloride solution, what will happen? The colloid is negatively charged, so it will attract the positive ion, that is Ba2 plus ions from the electrolyte. It will be neutralized, it will be settling, it will be precipitating at the bottom. Now, if I am using aluminum chloride, if I am adding aluminum chloride to this negatively charged electrolyte, what will happen? This negative electrolyte will attract the Al3 plus ions from the electrolyte and it will be neutralized and it will be coagulated. So, here the negatively charged colloid is neutralized by Na plus, here it is neutralized by Ba2 plus, and here it is neutralized by Al3 plus. So, among these three electrolytes, the most efficient electrolyte for coagulation is Al3 plus or AlCl3. The reason is higher the charge, higher will be the coagulation power. This is what is explained by using Hardy-Schulz rule. So, according to Hardy-Schulz rule, greater the charge on the electrolyte, greater will be the coagulating power. And the ion responsible for the coagulation is known as coagulating ion or flocculating ion. So, if it is a negative colloid, if the colloid is negatively charged, the coagulating ion will be positive. If the colloid is positively charged, the coagulating ion will be negative. And higher the charge of the coagulating ion, higher will be the coagulating power. Now, so this is what is explained here. If it is a negatively charged colloid, if we are treated with NaCl, barium chloride and AlCl3, AlCl3 will be the best coagulating agent due to higher charge. Now, coagulating power is actually, it is the minimum amount of electrolyte required to cause precipitation or coagulation. So, lesser the amount required, higher will be the coagulating power or higher the coagulating value. And the last one is the protective colloids. Lyophilic colloids are also known as protective colloids. The reason is the lyophilic colloids can be used to protect lyophobic colloids because they can form, because lyophobic colloids, they don't have a protective layer of solvent because they are solvent hating. When we add lyophilic colloid to a lyophobic colloid, this lyophilic colloids will be forming a protective layer around lyophobic colloids. So, that is why they are known as protective colloids. The coagulation of the lyophilic salts, coagulation of lyophilic salts can be done by adding electrolyte or by adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic salts, the dehydration of dispersed phase will occur. So, this is about the properties of colloids. Thank you.